Okay, everybody ready to go? Last time we finished up class talking about ISP ranges for the various types of rockets used for in-space propulsion and kind of compared their corresponding exit velocities to various delta V's associated with missions. So just to refresh your memory, there's a wide range of delta V's necessary for different missions. So to optimize the delivery of a payload to the destination requires selection of the correct type of propulsion system. So today I'm going to pick up from where we left off, and we will finish at this introduction to in-space propulsion. And because we are looking at EP devices that operate on gases or using gases that are electrically conducting, we will switch into an introduction to Maxwell's equations and electromagnetism towards the end of lecture today. All right. So if we look at the kinetic energy in the exhaust of a rocket motor, that is given by epsilon sub k for kinetic energy is equal to 1/2 times the mass times the exit velocity squared, and the thrust power is then given by, call it P sub t, is equal to 1/2 times m dot times the exit velocity squared. This assumes a constant average exit velocity u sub e. And if we substitute in for m dot, that is simply RT, m dot times u is the thrust, so that's m dot RT times the exit velocity divided by 2. And we can substitute, velocity is not squared. This is also equal to 1/2 m dot, and if we substitute for the u squared, that would be gravitational constant at Earth's surface times the specific impulse squared. Thus, although high ISP results in higher payload fractions.
Is that M or M dot?
This is an m dot, sorry. Okay, so we last time showed that we get higher payload fractions from higher ISP. The drawback is that there is a significant power penalty.
Yes.
I should make it a reminder. if we look at the power requirement for that thrust or an electric propulsion system, we have to provide that through some power source, electric power source. Okay, often, well, we say usually, the power available drives the design of the EP system. So it's typical, at least in Earth orbit, that you've got solar arrays on satellites that are typically going to be limited to on the order of 30 kilowatts. And so that kind of puts the limit on what you can do with a thruster. Let us discuss something called the power supply penalty. The solar arrays or whatever our power source is give us electric power at some potential, some current level, and that may not be what is required for the thruster type that you're using, so that has to be processed. And a power processing unit that conditions the electric power to the form needed by the thruster. And so that conversion itself, system itself has a mass and volume associated with it. And if you were using a chemical rocket, you wouldn't have one of those power conditioning units. So this serves as a penalty on the EP side of things when you're doing comparisons in various thrusters for particular missions. And so that is the topic of this section, the overall efficiency of an EP system is often called the thrust efficiency and this is defined as the thrust power divided by the total electric power required. So we will call that thrust efficiency 80, eta, and this would contain a large part of that power conversion efficiency. And this is equal to the thrust power. Thank you. T thrust times the exit velocity divided by 2, which is the thrust power divided by the overall electric power. If we assume a mass of the power supply is proportional to the power used, And here, this power supply is what I was referring to as some kind of power conditioning unit. In the industry, they'll call them PPUs, power processing units. Okay, so this is typically thought of as being proportional to the power used. Okay, and an equation for that is mass of the power supply, M sub P. Please don't confuse that with propellant. Okay, M sub P is equal to alpha times the electrical power, which is equal to alpha times thrust times exit velocity divided by 2 times eta. We'll define these terms in a second. And this is further equal to alpha times m dot, and we will replace exit velocity squared with g naught times specific impulse squared divided by 2 eta. That should be equation 9 in your textbook. Where here we have that this alpha is defined as the specific mass of the power plant. And typically what you will see for units of this would be kilograms per kilowatt. Okay. For a given mission requiring a total thrust time of delta T, the total mass of the propellant is so this delta M is total mass of the propellant used in a mission is mass flow rate of the propellant, delta or dot m dot times delta T. M dot is the same thing as thrust divided by the exit velocity, and we multiply that by delta T. And so substituting in for the exit velocity, we have thrust times mission time, or thrust mission, and divided by the specific impulse and gravitational constant. And notice that this delta M is inversely proportional to the specific impulse. for a given mission. Okay. So, as ISP goes up, our payload fraction will go up. More mass available for the payload because we don't need as much propellant. But then as we go up in specific impulse, the power goes up, right? So we have this weight penalty that is working against us. So that means there'll be an optimum value of the specific impulse. So there is an optimum value of the specific impulse for a given mission to deliver the maximum payload as shown in figure 1-1. And that's on page 8 in the textbook. So there is that figure. So we have mass of the system plotted as a function of ISP. So this delta M is the required propellant mass for a specific mission with some time delta T. And so as ISP goes up, mass drops. But the mass of our power supply goes up with ISP. So obviously we get some optimum value with the sum of those. And that value occurs at, we'll call I sub S hat to represent the optimum. And that turns out to be 1 over G naught times 2 times the conversion efficiency eta times delta T over alpha, and that ratio is raised to the 1/2 power. That's equation 10 in your textbook. Okay. This is not the whole story. However, in the 1990s, and I think I mentioned this in the last class, the total time to affect an orbit transfer particularly for military satellites. Prevented the rapid adoption of EP. The low thrust levels just kind of made it impractical to get satellites where you wanted them in a short enough time. Okay. And why is that a problem? Why is that a limitation? This is because the power required is directly proportional to the thrust. So P is equal to, once again, thrust times gravitation constant times specific impulse divided by 2 divided by the conversion efficiency.
Push the paper.
Ah, thank you. And the available power is usually limited to a few kilowatts. Because of the size of solar arrays required. Okay, thus power supply weight is very important for practical use of EP. And 3 important points emerge. Okay, the first one. For a given specific power plant mass, operation at either too high or too low ISP will reduce payload fraction. That's the way that paper wants to curl up. Okay, the second important point is that the overall conversion efficiency which was eta, becomes very important. And the last important point is that development of low specific mass space power plants is as important as the development of high ISP thrusters. We like to think of ourselves as rocket scientists and doing all that's really fun when we're at the mercy of the electrical engineers and power engineers to make it possible for us to play. Well, we owe them a debt of gratitude. Okay. Section 1.3. Definition of electric propulsion. Okay. The thrust power. This is the third time we'll have written this down, so you should remember it. The thrust power is proportional to the mass flow rate. Okay, so thrust power is equal to 1/2 times propellant flow rate U dot, or M dot, excuse me, times UE squared. And the power available in a chemical reaction is also proportional to mass flow rate. So we can say P sub C for the chemical energy is equal to an epsilon sub C times M dot, where epsilon sub C is the specific energy of combustion. if we define a constant alpha, and we're going to define it as the fraction of the energy converted to thrust. The fraction of alpha is converted to thrust. Then the exhaust velocity attainable is limited to so we have some maximum exit velocity is equal to the square root of 2 times alpha times epsilon sub c. And remember, this is for a chemical rocket. So that's our limiting case, because that will limit our ISP, just divided by G, and there we go. Other means must be used to increase the exhaust velocity above this limit. External power sources. Can be used to increase the gas temperature. Above that possible with chemical energy release. Some candidates for providing this energy are nuclear fission or fusion, and electrical heating. These methods can lead to rocket motors with ISPs in the range of 1,000 seconds. Okay, but further increases requires non-thermal processes. Okay, so let's think about this a minute. Basically, the heat of the temperature associated with combustion, um, release of energy is what defines the upper limit for the exit velocity in the thermal expansion. So we use nuclear energy, but we could use it to drive that to even higher temperatures. Same with electrical heating using arcs or resistive heaters. Why then would we be limited to basically 1,000 seconds? Because that implies a temperature on the order of 2,800 Kelvin or so. So what's the limiting factor? You can always add more heat to a gas. Our problem becomes materials. And so you have to have a nozzle with an expansion in the nozzle throat, and refractory metals start to become soft right about 2,900 Kelvin to 3,000 Kelvin. So materials limitations prevents this from going to a higher level. It's not a limitation of the thermal expansion itself. It's like one of those things, all problems in engineering go back to materials problems. So we can always blame our limitations on the material scientists, which is nice. So in this class later on, after we learn a little bit about electricity and magnetism, we will look at thermal processes in arc jets and resistive jets and other electrothermal devices. And then we'll be moving on to like electrostatic and electromagnetic systems that kind of divorce the thrust from the thermal processes so you can get to those higher ISPs. All right, so I started off this section saying we were going to define electric propulsion, and all we did is say why chemical is limited and give a feel for what the maximum performance is associated with electrothermal devices. Our author, Robert John, or as those of us like me who had the privilege of meeting him at a banquet one time and shaking his hand, I can call him Bob now. Bob John's definition. For electric propulsion. Put this in quotes. It is the acceleration of gases for propulsion by electrical heating okay, by electrical heating and or by electric and magnetic body forces. So that's what John wrote in 1968. This definition might be expanded. To include macro particle acceleration, for example, solid propellants accelerated by electromagnetic rail guns or rail launches, or some people have looked at using macro particles such as taking a buckyball, which is carbon 60, and replacing one of the carbons or attaching an ion to it so that it has a charge that you can use to accelerate. And when we talk about electrostatic acceleration, I will go over that again. It'll become clear as to why that's beneficial. Okay, so the range of possibilities. Oh, one other thing I was going to mention. Another thing that you could do is some people consider laser propulsion an electric propulsion because you use electricity to drive the laser, and the laser can be used to ablate a propellant or actually be used as onto a mirrored surface to provide a driving force. But those are pretty advanced concepts that don't have many practical uses at the time. The ranges of possibilities is often divided into three categories. So these are possibilities of EP. Into three categories, which are mutually exclusive. Okay, the first one of those is electrothermal propulsion. That's what we've been discussing quite a bit of so far. And in electrothermal propulsion, we have a gas is heated electrically. And then expanded in a nozzle. Okay, this is identical to chemical propulsion except for the energy source. Second category is electrostatic propulsion. Where the propellant is accelerated directly by applied electric body forces. Okay, the classic example is the ion engine. And finally, we have electromagnetic propulsion. And this is where the propellant is accelerated by magnetic forces. And those magnetic body forces are themselves produced by current passing through the propellant. Okay, these three categories are presented in an increasing order of difficulty. Okay, at least where from an engineering perspective. And the order also represents the order in which commercial application has followed. It's important to note that that's commercial applications. The first electric propulsion system was a pulse class thruster, and that's an electromagnetic device, and one of the more complicated of the groups. And the first EP systems to be widely used for satellites or arc jets, which are electric devices. And then later on, we started adopting ion engine and Hall thruster technologies even though they were developed, some of those were developed early on. It's just that the commercial entities didn't want to take the risk. While I'm on that topic, how did engineers and scientists convince, turned out to be the military, that electric propulsion made sense, at least electric thermal devices? Because these folks wanted to be able to move their satellites around quickly, relatively quickly. They didn't want to have any system failures from these unknown devices or not checked out that would cause $1 billion satellite to become non-operational. And they also wanted to save propellant mass. So in that respect, the EP devices were really attractive, but they were concerned about reliability. You have hardware in space that is critical to the defense of our country. And so they wanted to make sure these things are reliable. So what these guys did is they said, well, we're going to start with something called a resistive-jet. And so what we do is you take a propellant, and usually that propellant is hydrazine, really nasty stuff that we'll talk about later. Hydrazine is N2H4, ammonia is NH3. Hydrazine is toxic, caustic, causes all kinds of problems. You have to be wearing hazmat suits to deal with the stuff. What's positive about hydrazine is that if you float over a catalyst, it breaks down and releases heat. Okay, it heats up the propellant, and you can expand that out of the nozzle and produce thrust. Okay, so that doesn't even require electrical power. So if you add the electrical heat through resistors, that's a resistive-jet, you can boost the temperature, you get better performance, both in thrust and in ISP. So the generals and people making decisions were convinced that even if the electrical circuit side of this in-space rocket system failed, they still had a reasonably reliable cold gas thruster. Okay, so that's how the concept was sort of sold. And so satellites started being launched with these things, and they proved out the technology, and now it's commonplace. So what engineers and scientists on the ground doing testing already know can be very difficult to convince commercial entities to adopt, just because they're driven by profit or mission readiness in the case of the military. Okay. Any questions about that? All right, I got off topic just a little bit, but so we have these three main categories: electrothermal, electrostatic, electromagnetic. It is important for us to point out that not all devices fall in just in one category. Right? So in some devices, two or more of these processes may contribute to the acceleration. For example, in magnetoplasmodynamic thrusters. You don't need to worry about writing out that complete name. We'll fit well into this stuff when we're doing electromagnetic devices. But in these MPD thrusters, which they're usually referred to because people don't like to say magnetoplasmodynamic, I guess. These are essentially part electromagnetic and part electrothermal. So part of the thrust is thermal. And part is electromagnetic. Okay, another example in the Hall thruster. Acceleration can be analyzed as electrostatic. Or electromagnetic. Okay, people like to argue one way or the other. When we get to the topic or section, we'll argue that it's both at the same time. Okay. Often devices are more pure. Okay, the arc jet is normally thermal. And the ion thruster is essentially electrostatic. Often, devices such as the pulse plasma thruster referred to as a PPT are conceptually electromagnetic. But in fact are more nearly electrothermal. And this last point, if I had right people in the audience in this classroom, they'd be yelling at me now. When I was a graduate student, I saw my advisor at the time get into an argument in the middle of a section of a joint propulsion conference on electric propulsion devices, specifically PPTs, arguing about whether their thrust was produced by electromagnetic or electrothermal processes. Like it really matters, but it was, you get some of these older crotchety type faculty members that are set in their ways and they don't like it when you change their nomenclature. So I don't know. This here could be fighting words. So just be careful when you go forward. Okay, let's finish this chapter up. I'm serious. I thought they were going to use like, if I didn't know my advisor better, I could. They could actually throw punches if this goes on much longer. Okay, nearly all EP devices utilize plasma propellants. Since electromagnetic interactions with gases are only strong when the gases ionized. Okay, so that means that electrons are free to move under the influence of electromagnetic fields. Therefore, there is a point to this. Therefore, we must begin with a study of electricity and magnetism. And you will see that written a lot as E and M. And we also need to look at properties associated with ionized gases before things can be applied directly to electric propulsion technologies. Okay, we are at the end of the first chapter in John's book. I will be assigning a few of the homework problems that are given in the book. I'll do that through Canvas so everybody has the right information and I don't have to worry about writing down the wrong stuff here and screwing things up. And so you should have those in your email. So we provided a nice segue to the next topic, electromagnetic theory. Okay. Almost everybody in this class has an engineering background as an undergraduate. And so you're used to seeing things like Ampere's law and Faraday's law. in nice discrete forms that allow you to calculate forces and fields on circuits. We're not going to do that here. We're going to take those for Maxwell's equations, and most of you have probably seen what they are and then quickly forgot them because you didn't have to apply them for anything. So we're going to be doing some applications, and I don't want it to sound scary. I'm going to start from the beginning of the basics. Electromagnetic phenomena all result from electric charges. Particles in nature are composed of subatomic particles. Told you I was going to start basic. Okay, and some of these carry a discrete charge. And that happens to be denoted as a lowercase e, and it's 1.6 plus a bunch of other additional significant figures, times 10 to the minus 19 with units of coulombs, capital C. Atoms are composed of electrons, which have a charge of minus E, protons, which have a charge of plus one fundamental charge, and neutral particles called neutrons. Shut the paper up. All electromagnetic phenomena result from the forces and magnetic fields produced by the distribution and motion of these charges. Okay, historically speaking, these effects were discovered over a period of time and consolidated by Maxwell. into a uniform or a unified mathematically simple and elegant theory. Which describes all electromagnetic phenomena. Okay. Maxwell's equations. Are as fundamental as Newton's laws. And can form the axiomatic basis of electromagnetism in the same way as Newton's laws. Are the basis of classical mechanics. Okay, we're almost finished. Bear with me for a couple more minutes, please. However, the subject of electricity and magnetism is usually taught in a chronological manner. Starting with electrostatics. Then magnetostatics. And finally, magnetodynamics. Okay, we'll stop there. The next time we will write down Maxwell's equations and look at the force of a charged particle in an electric field and build from there. Anybody have any questions? As far as the homework goes, you'll get those posted. I will probably make them do a week from Friday since I'm going to give you at least a couple of class periods to work on. Okay. If anything comes up before we meet again on Friday, just reach out to me. See you then.